Say we're working at a nuclear power station, so we've got some kind of nuclear reactor and there's some kind of radioactive material involved. Then the symbol we normally use for the activity of this material, and activity just means the number of radioactive decays that happen per second. So we just use capital A to represent the activity, and the unit would be becquerel, but we don't need to worry about that for this particular question. Okay, so we've been told that the rate of change of decay, in other words dA by dt, is equal to negative lambda A. So lambda is known as the decay constant. And then we've been asked to find an equation for A in terms of time t. So the first thing we need to do is get anything involving a t, and there's only one thing in this case. We need to get that on the right hand side of the equals, and anything involving an a we need to get on the left hand side of the equals. So what we do to begin with is we multiply everything through by dt, and that brings the dt up on the right hand side. Then we divide through by capital A, so that gives us dA over A equals negative lambda dt. Now when you get something like this, it's often helpful to rewrite it like this. So all I've done is, this thing here is the same as this one, but we just rewrite it as 1 over A dA equals negative lambda dt. Then we simply write integration symbols in front of each side of the equation, and now we're ready to integrate. So if you remember, 1 over A is a special case. If you remember, 1 over x integrates to the natural log of x, or ln x. So this is just going to integrate to, it's actually not ln x, it's the ln of mod x. So this will integrate to the ln of mod a. So that's just, if a was negative, these two lines just say, well, make it a positive number. That's all that does. Negative lambda, well, we know lambda is a constant and we're integrating with respect to t. So that just gives us negative lambda t plus c, the constant of integration. Now, as it happens, a can never be a negative number. You can't have a negative activity. So we can get rid of these two lines. And that just gives us ln a equals negative lambda t plus c. So let's go over to page 2. So we've ended up with ln a equals negative lambda t plus c. But we want to get a on its own. And the way to do that is to remember that the opposite of ln is e to the power. So what we do is we rewrite the equation above like this. We do e to the power of the left-hand side is equal to e to the power of the right-hand side. And remember, the reason we've done that is e and ln are the inverse functions of each other. So the e and the ln will cancel out, leaving us with this. A equals e to the minus lambda t plus c. But when we've got powers added up, we can actually rewrite that like this. E to the minus lambda t multiplied by e to the c. But as c is a constant, e to the c must be a constant as well. So we can say, well, let's call e to the power c equal to a0. And then this equation, I'm going to call this bit a0, can be rewritten as a equals e to the minus lambda t a0, which we normally rewrite like this.